Let's look at OpenStax University Physics Volume 2, Chapter 12, Problem 42. Evaluate integral b dot dl for each of the cases shown in the accompanying figures. So, first of all, we're being told to evaluate an integral that we don't know what it is. It actually is sum b parallel delta L, and we know this as Ampere's law, and this other side of the Ampere's law says that it's mu naught times I enclosed. So basically we want to know what this quantity is. It's the equivalent to that. So this quantity is equal to mu naught times I enclosed. We have in all of these parts Amperian loops already drawn and directions for them given, so we can apply Ampere's law to figure out what mu naught times I enclosed is. So starting with the first one, first we want to check the direction. So if the current goes in this direction, placing our thumb in this direction and then curling our fingers around will give us the same direction. So when we do sum of b parallel delta L, we get a positive number. Now, what is enclosed in this Amperian loop? Well, just this 2 amp current, so we'll multiply mu naught times the I enclosed. So let's write this here. So sum b parallel delta L is mu naught I enclosed. So that is 4 pi times 10 to the negative 7th Tesla meters per amps times the 2 amps current, and that gives us 2.51 times 10 to the negative 6th Tesla times meters. So that is the answer to part A. Now for part B, we look and see that there are 3 different currents. The 5 amp and the 6 amp go up, the 2 amp goes down. So if I do the right-hand rule for the currents going out, so either the 5 amp or the 6 amp, I place my thumb in this direction, my hand curls around in this direction, so this would be the positive direction along which we would integrate or sum. And that means that these currents are positive and that current will be negative. So when we write sum of the magnetic fields parallel times delta L is mu naught I enclosed, then the I enclosed is going to be mu naught, or 4 pi times 10 to the negative 7 Tesla meters per amps, times the current enclosed, that is 5 amps minus 2 amps plus 6 amps. And when we multiply the numbers, we get 1.13 times 10 to the negative 5 Tesla meter. In part C, we notice that there is no current enclosed by the Amperian loop. The currents on the outside do not matter. We want to know what the magnetic field is in this closed loop, then magnetic field is 0. So I enclosed is 0, so that means that B parallel delta L is also 0. Now in part D, we have 3 currents. This one is outside of the loop, so we only look at these 2 currents, the 2 amp and the 4 amp. And then we have to decide which ones of these give me a positive value for the magnetic field. So if I place my thumb in the direction of the 2 amp current, then my fingers will rotate around in this direction. So that is the opposite direction, so this is the negative current. If I place my thumb in that direction, then my fingers will curl in this direction, and that is my positive current. So when I write sum of the magnetic fields parallel delta L is mu naught I enclosed, that will be 4 pi times 10 to the negative 7 Tesla meters per amps, and the 4 amp current is positive, 2 amp current is negative, and when we multiply them, we end up with 2.51 times 10 to the negative 6 Tesla meter. For part D, now we have 4 currents, but only these 2 are in the Amperian loop. So only the 3 amp and the 2 amp current matter here. They're both in the same direction. So we'll place our thumb in the direction of the current, and our fingers will rotate counterclockwise, which means that that's going to be in the opposite direction from the direction of integration or summation. So that means that we're going to get both of these currents as negative. So we'll have sum B parallel delta L is mu naught I enclosed. So that will be 4 pi times 10 to the negative 7 Tesla meters per amps times negative 3 amps times negative 2 amps. And we'll get negative 6.28 times 10 to the negative 6 Tesla meter.